Everyone, in this video we're going to talk about pH and pOH. So one of these you're probably really familiar with, the other you're probably not as familiar with. pH is commonly the measure that we use to determine how acidic or basic something is. So pH is actually a measure of the amount of hydrogen. And because of our Bronsted-Lowry definition, we know that if there are more hydrogens present, we basically have more acids present, or we have more of an acidic environment present. pOH is a measure of the amount of OH. And so this lines up more with the Arrhenius definition, which is why it's not used as much anymore. Again, we said that exception of ammonia, the NH3, is a base, but it doesn't have any hydroxides in it. But these two can be used often to determine and describe what the environment is like. And so pH has a typical scale where it goes from 0 to 7 to 14. At 0 to 7, this is the acidic stage. 7 is neutral, and anything above 7 we would consider a basic environment. And so human blood is right about a pH of 7.4. And so what I always tell my students is that if someone calls you basic, you can say, thank you, yes, in fact, my blood is at a healthy pH. And that can be your counter to that insult. pOH is slightly different in the fact that it is the reverse. That at a pH of 0, we have something that is really, really basic. At 7, it's still neutral. And at 14, it is acidic. Again, we're measuring the amount of hydroxides present. And so if we have more hydroxides, we would say then that substance would be more basic. And so out of that, from pH and pOH, there's a couple formulas that we can use. So all of this stems from this idea that if you have a solution of water, if you have a solution of H2O sitting around at any given point in time, it can perform this reaction where we end up with H3O and we end up with an OH minus aqueous. And for us, we wouldn't ever be able to tell that this reaction is happening because we would generate an acid, which is the H3O, which is known as hydronium, and we'd generate an OH base as well. And so because there'd be equal concentrations of the H3O and the OH, they would just neutralize themselves and it would cancel out. But at any given point in time, that glass of water that you're drinking looks like this. There are these reactions constantly happening, going on in that glass of water. And so what we can do then is we can figure out a formula to figure out how acidic something is based on this amount of H3O. And so the formula that we're going to use is we can calculate the pH by going the negative log of H3O plus, the concentration of H3O plus. And as this concentration of H3O plus rises, what we will see is that this pH number will get lower because of how logarithms work. There is also an inverse formula that you can use as well. Let's say that you need to figure out the concentration of H3O plus. What you can do is you can say, well, the inverse log is 10 to the power of something. We assume that this log is at a base, and then you take the negative pH up top there, and you figure out the concentration of H3O. Now, some people will replace these H3Os with just an H+, and for our purposes, that's fine. If it's H+ or H3O, you can count those as the same sort of concentration. It's sort of a confusing area where some scientists use and prefer this H3O, some prefer the H+, but for our purposes with this formula, either the H3O or the H+ is fine. Now, if we have those two formulas, what that means is we also have a pOH formula as well, and we can use the pOH of negative log of the concentration of OH minus, and that'll give us the pOH. In the same mindset, we can reverse that formula and take 10 to the power of the negative pOH, and we can solve for any one of those variables. Now, the beauty of having a pH and a pOH is that because they're reverses of each other, we know that the pH plus the pOH should always equal 14. So if you have a solution with a pH of 1, like your stomach acid, we would assume the pOH of your stomach acid would be 13. In other words, it would be really high on the scale, acidic. pH, it would be really low on the scale, acidic. Again, pH and pOH communicate sort of the same information, but in reverse ways. And because pH lines up better with the Bronsted-Lowry definition, it's the preferred method that we use more often. And that is the formulas of pH, pOH, and the descriptions and definitions between them.